Researchers Gabriel Rondón, Paulo R. da Silva, and Luiz F.S. Gouveia investigate the existence of invariant complex manifolds in two-dimensional holomorphic slow-fast systems. Building on geometric singular perturbation theory, they explore the conditions under which a normally hyperbolic compact critical manifold guarantees the existence of a smooth, locally invariant manifold. However, the existence of a complex structure on this manifold is not guaranteed. To address this, the authors provide conditions for the existence of unidimensional invariant complex manifolds in two-dimensional holomorphic systems in R to the power of 4. These systems can be represented by the system SF, Z equals F, Z, W, and W equals G, Z, W, where F and G are holomorphic functions defined on a simply connected domain D subset of C squared, and epsilon greater than 0 is a small parameter. The authors draw on techniques from Fenichel and Briot-Bouquet theories to establish the persistence of centers, foci, and nodes in the reduced problem via singular perturbation. The authors' work contributes to the qualitative theory of dynamical systems, where singular perturbation problems have been extensively studied. Notably, two-dimensional holomorphic systems have received limited attention in the literature, despite their applications in various fields. By investigating the existence of invariant complex manifolds in these systems, the authors aim to bridge this knowledge gap and advance the understanding of complex dynamics in slow-fast systems. The study focuses on the conditions that ensure the existence of a complex structure on the invariant manifold, enabling the authors to establish the persistence of critical points in the reduced problem. This research has implications for the analysis of complex systems in various fields, where the existence of invariant complex manifolds can provide valuable insights into the system's dynamics. The existence of invariant complex manifolds for two-dimensional holomorphic systems, particularly system SF1, is investigated in this study. Notably, Fenichel's theorem fails to guarantee the existence of such manifolds due to the requirements of even dimension and orientability. To overcome this limitation, the authors employed geometric singular perturbation theory and Laurent series to construct examples of smooth manifolds lacking complex structure. A complex dynamical system, 1, with a normally hyperbolic critical manifold C0 is presented as an illustrative example. The equivalent system in R4 is shown to possess a smooth locally invariant manifold S, but crucially, it lacks a complex structure. This is demonstrated by assuming the existence of a holomorphic function H, and subsequently expressing it as a power series. The authors highlight the limitations of Fenichel's theorem, emphasizing the importance of considering the specific properties of the system when studying invariant complex manifolds. By doing so, they underscore the need for a more nuanced understanding of the interplay between system dynamics and manifold properties. The paper delves into the existence of complex invariant manifolds in two-dimensional holomorphic slow-fast systems, concentrating on the conditions under which these manifolds can be guaranteed. It initiates by introducing a system, SF1, and its associated series, which diverges for W equals 0, contradicting the fact that H, W, is holomorphic. In Section 3, the authors utilize the Briot-Bouquet theory to provide conditions for the existence of unidimensional invariant complex manifolds. They prove in Theorem A that, for epsilon greater than 0 sufficiently small, the system, SF2, has a unique unidimensional invariant complex manifold C, passing through the equilibrium point Q equals 0, 0, provided that the critical manifold is normally hyperbolic. The authors then employ Theorem A to show that the centers, foci, and nodes of the reduced problem associated with the holomorphic slow-fast system, SF1, whose Jacobian matrix of F and G is diagonalizable at the origin, are preserved by singular perturbation. This preservation is detailed in Theorem B and visually represented in Figure 1. Furthermore, the paper addresses the existence of complex invariant manifolds for certain families of two-dimensional holomorphic systems, where the Jacobian matrix of F and G is not necessarily diagonalizable at the origin, and this point does not need to be an equilibrium point of the system. Theorems C and D are presented to provide conditions for the existence of such manifolds in these systems. In this research paper, the authors explore the existence of unidimensional invariant complex manifolds associated with slow-fast systems. These systems are characterized by equations of orbits that can be written as a product of holomorphic functions, which are complex valued functions defined in a domain V subset equals C and satisfy certain continuity and differentiability conditions. The concept of a complex manifold is introduced as a set of points that can be mapped to a domain in C using a holomorphic function. The paper is organized into 5 sections. Section 2 provides preliminary results on complex manifolds, geometric singular perturbation theory, and the Briot-Bouquet theory. Sections 3 and 4 employ the Briot-Bouquet theory to prove theorems A, B, C, and D, establishing the existence of invariant complex manifolds under specific conditions. The authors also present a method to study slow-fast systems of a specific form, where the right-hand side of the equation is a function of the complex variable W. In sections 3 and 4, the authors prove the persistence of centers and poles of order n of the reduced problem associated with system SF4 under singular perturbation. This means that the behavior of these singularities is preserved when the system is perturbed. Finally, section 5 uses Laurent series to provide examples of complex systems without associated complex manifolds, further illustrating the nuances of this theory. In the realm of complex analysis, a function f V right-pointing arrow C defined on an open subset V of the complex plane C is considered holomorphic if it satisfies the Cauchy-Riemann equations. These equations involve partial derivatives of the function with respect to its real and imaginary components, u and v, respectively. The Luhmann-Menchoff theorem establishes that these conditions suffice to guarantee the analyticity of f. A key concept in this context is the Laurent series, which represents a function around a singularity, such as a pole or essential singularity. A pole of order n occurs when there exists an integer n greater than 1 such that Bn does not equal 0 and Bk equals 0 for all k greater than n, where Bk represents the Laurent series coefficients. An essential singularity, on the other hand, is characterized by an infinite set of non-zero Bk coefficients. The notion of holomorphy can be extended to higher dimensional spaces, specifically to open subsets W of C squared. In this case, the Cauchy-Riemann equations must hold for each coordinate zj equals xj plus iyj, with j equals 1, 2. Furthermore, if f is holomorphic in W, then for every point xi, element of W, there exists an open neighborhood D, xi, such that the function f can be expanded into a power series, which converges for all z, W, element of D, xi. The definition of a complex manifold also parallels that of a smooth manifold, with the requirement that charts take on values in C squared and that the transition functions be holomorphic. This structure allows for the study of complex geometric objects and their properties. Complex manifolds are topological spaces equipped with a maximal holomorphic atlas, consisting of pairs of open sets and holomorphic charts. Each open set UI is an open subset of the topological space X, and each chart I is a homomorphism from UI to an open set in Cn, where n is at least 2. The transition functions ij between charts are required to be holomorphic maps. The complex dimension of the manifold X is denoted by n. A key concept in complex geometry is the notion of complex submanifolds, which can be obtained using a holomorphic map between complex manifolds. Proposition 1 states that if is a holomorphic map from X to C, and B is a point in the image of such that the rank of is maximal, then the pre-image 1, B, is a complex submanifold of X of dimension 1. The paper then explores geometric singular perturbation theory, which deals with singularly perturbed systems of differential equations, also known as slow-fast systems. These systems take the form of equations, 2, where x and y are functions of a variable, and is a small positive parameter. The functions f and g are assumed to be CR and defined on an open set M in R4. The dot notation represents the derivative of x and y with respect to. Holomorphic slow-fast systems are represented by the system of equations, 2, where t is a parameter representing the ratio of timescales. By setting t equals tau, the system becomes 3. Where the apostrophe denotes the derivative of the functions x, t, and y, t, with respect to the variable t. The reduced problem is obtained by setting tau equals 0, resulting in the algebraic differential equation, 4, which is not an ordinary differential equation. The solutions of 4 are contained in the critical set C0, a set of points where f, x, y, 0, equals 0. When C0 is a manifold, it is called the critical manifold. The layer problem is obtained by setting tau equals 0 in equation 3, resulting in the system of ordinary differential equations 5, where y is a parameter and the critical set C0 is a set of equilibrium points. The main goal of geometric singular perturbation theory is to study systems 4 and 5 to obtain information about the full system 2. Systems 2 and 3 are equivalent when tau greater than 0, since they only differ by timescale. A point x0 in a set S subset equal M is said to be normally hyperbolic if the 2x2 matrix df x0 does not have eigenvalues with 0 real part. According to a version of Fenichel's theorem, if C0 is a crossing submanifold of M consisting entirely of equilibrium points of x0, and S subset equal C0 is a J-dimensional compact normally hyperbolic invariant manifold of the reduced vector field XR, then there exists a locally invariant manifold of the full system, 2, that is diffeomorphic to S. This theorem's proof can be found in reference 16. Normally hyperbolic invariant manifolds are a fundamental concept in dynamical systems theory, particularly in the context of slow-fast systems. A normally hyperbolic invariant manifold is an invariant manifold that remains stable under perturbations, a crucial property for understanding complex system behavior. Two theorems are presented to describe these manifolds. Theorem 2 states that a normally hyperbolic manifold S can be locally represented as the graph of a function of x in terms of y. This result provides an explicit description of the manifold, enabling further analysis of its properties. Theorem 3 builds upon Theorem 2, asserting that under certain conditions, there exists a function x equals h, y, defined on a compact domain K, such that the graph S equals x, y, x equals h, y, is locally invariant under the slow-fast system. This means that the manifold S is preserved by the system's dynamics, a key property for understanding long-term trajectory behavior. The page also explores two-dimensional holomorphic slow-fast systems, where functions f, z, w, and g, z, w, are holomorphic functions of complex variables, z, w, equals x1 plus iy1, x2 plus iy2, in a domain D. The fast system is given by equations 6, and the critical set C0 is defined as the set of points where f, z, w, equals 0. The reduced problem is given by equation 7, and the layer problem is defined as equation 8. These results provide a detailed understanding of normally hyperbolic invariant manifolds, their properties, and their relationship with slow-fast systems. This information is crucial for researchers in dynamical systems, as it helps in understanding the stability and behavior of complex systems. The paper explores the concept of normal hyperbolicity in complex systems, particularly focusing on holomorphic slow-fast systems and Briot-Bouquet systems. It begins by introducing a system, SF1, with a singular perturbation parameter, greater than 0, which is equivalent to another system, 6, when greater than 0. This equivalence allows for the study of system, SF1, through the analysis of system, 6. The Jacobian matrix of the system in R4 associated with 6 at an equilibrium point Q0 equals Z0, W0 is provided, showing that the eigenvalues of the Jacobian matrix are given by zeta equals U1 x1 plus I V1 x1. A subset S subset equals C0 is defined as normally hyperbolic if Re F Z Q equals U1 x1 Q does not equal 0 for all Q in S. The paper then moves on to discuss Briot-Bouquet systems, which are a class of unidimensional systems of the form ZW equals F, Z, W, where f is a holomorphic function and the apostrophe denotes the derivative of the function w, z, with respect to the complex variable z. A key result from the literature, proposition 4, is cited, stating that if f, z, w, equals zeta w plus o, z, w squared, and zeta does not equal 2n, then the Briot-Bouquet system admits a unique holomorphic solution at z equals 0 satisfying w, 0, equals 0. Finally, the paper addresses the persistence of invariant manifolds in the context of singular perturbation. The goal is to prove that centers, foci, and nodes of the reduced problem associated with the holomorphic slow-fast system, SF1, are preserved under singular perturbation. To achieve this, the authors consider constructing unidimensional invariant complex manifolds using the Briot-Bouquet theory. They assume that the equilibrium point Q equals 0, 0 of the system, SF1, is located within the domain D and that the associated linearized system has eigenvalues that are diagonalizable at the origin. Complex systems exhibit intricate dynamics, which can be understood through the concept of normally hyperbolic critical manifolds. Consider a system of equations, SF1 and SF2, and define the critical set C0 associated with these systems. The critical set C0 is classified as a normally hyperbolic critical manifold if it possesses a non-zero real part of the eigenvalue of the Jacobian matrix. A fundamental theorem is presented, stating that under specific conditions, a unique unidimensional invariant complex manifold C exists, passing through the equilibrium point Q. This manifold is represented by the equation W equals h, z, where h is a holomorphic function within a ball B centered at the origin. The proof of this theorem involves a series of transformations, beginning with the initial value problem, 12. By converting this into a new form, 13, and then dividing by the eigenvalue, equation, 14, is obtained. The transformation process facilitates the identification of the unique invariant manifold C. To further analyze this manifold, two holomorphic functions p, z, and q, z, are defined. These functions are expressed in terms of the original functions tilde f, z, w, and tilde g, z, w, enabling a deeper understanding of the system's dynamics and the properties of the invariant manifold. The paper delves into the concept of slow-fast systems, with a particular focus on the case where the critical manifold C0 is a normally hyperbolic manifold. It is assumed that the eigenvalues of the Jacobian matrix of the system are of the same type, such as pure imaginary, real, or complex numbers with non-zero real and imaginary parts. A function f, z, is introduced, which converges in some neighborhood of Q, and has a zero at the origin. This function is utilized to rewrite the initial value problem for the slow variable z, 0 in terms of f. By applying the Briot-Bouquet criterion, the authors demonstrate that this new equation has a unique solution, which is holomorphic in a neighborhood of the origin. The paper then considers the holomorphic function h, z, w, equals wh, z, where h, z, is the unique solution obtained earlier. The set C is defined as the graph of h, z, and it is shown to be an invariant set for the system. The authors prove that C is a complex manifold of dimension 1 using the rank of the Jacobian matrix of H. In the subsequent sections, the authors provide a remark that the result still holds when the hypothesis about C0 being a normally hyperbolic manifold is replaced by a weaker condition. They also assume that the eigenvalues of the Jacobian matrix of the system satisfy certain properties, including being of the same type. This assumption allows them to define a new function, z, w, and use the implicit function theorem to deduce that C0 can be expressed as the graph of a function of z in terms of w. In the realm of two-dimensional holomorphic slow-fast systems, denoted as SF1, the authors explore the persistence of centers, foci, and nodes in a reduced problem. This system is characterized by functions f and g, which are holomorphic in a punctured disk D, 0, r, nf0 grams. A crucial assumption is made that the partial derivative of f with respect to w is non-zero for all z, w, in the critical manifold C0. This assumption allows for the application of the implicit function theorem. thereby representing the critical manifold C0 as the graph of a function of W in terms of Z. The main result of this section, Theorem B, states that under certain conditions, centers, foci, and nodes of the reduced problem are persistent by singular perturbation. This theorem relies on the eigenvalues of the Jacobian matrix of the system satisfying a specific hypothesis, H, and the parameter, being sufficiently small. To prove Theorem B, the authors first apply Theorem A to show that for greater than 0 small enough system, SF2, has a unique unidimensional invariant complex manifold C at Q. This manifold is given by the set of points, Z, W, such that W equals H, Z, where H is a holomorphic function in B, and H, 0, equals H0, 0, equals 0. The dynamics on C are governed by the equation _Z equals Z plus tilde F, Z, H, Z, which is denoted as Z. The authors then use the result from 4, Theorem 1.1, to conclude that and Z are zero-conformally conjugate. Since Z and Z are of the same type, the persistence of centers, foci, and nodes of the reduced problem associated with SF1 follows. This result has significant implications for understanding the behavior of these complex systems, particularly in terms of their stability and bifurcations. Furthermore, the authors discuss other families of holomorphic slow-fast systems, specifically uncoupled differential systems. They assume that the partial derivative of f with respect to W is non-zero for all Z, W, in C0, and apply the implicit function theorem to show that C0 can be represented as the graph of a function of W in terms of Z. This work contributes to a deeper understanding of the interplay between slow and fast variables in these systems, shedding light on the persistence of certain dynamical features despite perturbations. In holomorphic slow-fast systems, an open set U and a holomorphic function W equals zeta, Z, exist, satisfying f, Z, zeta, Z, equals 0 for all Z in U. The orbits of the system are governed by the equation dW, dz equals G, Z, W, F, Z, W. Assuming the existence of holomorphic functions phi and psi in a set B, a subset of C squared, such that G, Z, W, F, Z, W, equals phi, Z, psi, W, for all Z and W in B, we can infer from corollary 6.16 and 2 that phi and psi have primitives in B. Consequently, both phi and psi, as well as their inverses, have primitives in B. Integrating dW, dz equals phi, Z, psi, W, yields holomorphic functions f and g, satisfying G, W, equals F, Z, F, Z, equals phi, Z, and G, W, equals 1, psi, W. A theorem is stated, asserting the existence of a unidimensional invariant complex manifold C, associated with the slow-fast system, provided G, Z, W, F, Z, W, is separable. The manifold C is characterized by two properties. Firstly, the flow on C converges to the slow flow as approaches 0, and secondly, the dynamics over C is given by dz, dt equals G, Z, W. The proof of the theorem involves considering the holomorphic function H, Z, W, equals G, W, F, Z, and the set C, equals Z, W, G, W, equals F, Z. We show that C is an invariant set, and the rank of H is the rank of the matrix JCH, given by phi, Z, 1, psi, W. Since JCH has maximal rank 1, in each point of C, we conclude that C is a complex manifold of dimension 1. In slow-fast systems, characterized by differential equations with variables evolving at disparate rates, the critical manifold plays a crucial role. This manifold comprises points where fast variables attain equilibrium. The authors investigate the perturbation-induced changes to this critical manifold, demonstrating that the perturbed manifold remains proximal to the unperturbed one in terms of Hausdorff distance, with a deviation of order epsilon. This key finding is subsequently generalized to uncoupled slow-fast systems, providing a foundational framework for understanding the intricate dynamics of these systems. By examining the perturbed critical manifold's proximity to the unperturbed one, the authors establish a rigorous basis for analyzing the complex interactions within slow-fast systems. The significance of this research lies in its ability to elucidate the behavior of these systems, which are ubiquitous in fields such as physics, biology, and chemistry. The author's framework offers a powerful tool for researchers to better comprehend and predict the dynamics of slow-fast systems, ultimately contributing to a deeper understanding of the underlying phenomena. In the realm of dynamical systems, a subset known as holomorphic slow-fast systems exhibits both slow and fast dynamics. These systems are characterized by their equilibrium points and poles of order n, which persist under singular perturbation. This persistence is demonstrated through several examples in the paper, including one where the critical manifold lacks normal hyperbolicity. The function g, w, plays a crucial role in these systems, with different forms leading to distinct invariant manifolds, denoted as C. The paper also delves into coupled differential equations, where the critical manifold is defined by the equation z equals g, w, per gram. Here, the set of points satisfying the equation of orbits forms a unidimensional invariant complex manifold. Geometric singular perturbation theory is employed to find this invariant complex manifold, providing insight into the behavior of these systems. The paper's findings contribute to our understanding of complex dynamics and their persistence under perturbation, shedding light on the intricate interplay between slow and fast dynamics in holomorphic slow-fast systems. A unidimensional invariant complex manifold C is introduced, associated with the slow-fast system SF3. This manifold converges to the slow flow as the parameter approaches zero, with dynamics governed by the equation W equals G, W. The authors establish conditions for the orbit of system 21 to remain exponentially close to C, within a specific region R, defined by the inequality 2 equals G, W, G, W0, greater than 0. Here, G, W, is a function of W, and 0 is a small positive number. The manifold C is constructed using a holomorphic function H, Z. W equals Z plus 2, G, W, plus, and it is proven to be an invariant set. Furthermore, C is shown to be a complex manifold of dimension 1 through analysis of the Jacobian matrix JCH. The Hausdorff distance between C0 and C is demonstrated to be of order, indicating that C converges to the slow flow as the parameter approaches 0. This result provides critical insights into the behavior of slow-fast systems, particularly in regions where the normally hyperbolic manifold C0 is not present. The theorem offers valuable understanding of the dynamics of these systems, with applications in fields such as physics, biology, and engineering, where slow-fast systems are commonly encountered. The convergence of C to the slow flow as the parameter approaches 0 highlights the significance of this invariant manifold in understanding the complex dynamics of slow-fast systems. In the context of a differential system, the concept of a unidimensional invariant complex manifold C is introduced. This manifold is exponentially attractive on the set R equals F Z W in C squared. Re W greater than Im W greater than 0. Two conditions are defined for the manifold C. First, for each point P in C, there exists a point Q in C0 such that the distance between them is O, and second, for each point Q in C0, there exists a point P in C, with a distance of O. The authors prove these conditions and show that the dynamics over C are determined by the equations _W equals and _Z equals a change of variables is introduced as V equals ZH W, leading to the equation dV dW equals I, 2 grams, W, V. The solution to this equation with initial condition versus W0 equals Z, W0, H, W0 is given as V, W equals versus W0, express I, 2, G, W, G, W0, and V, W equals V, W0, express I 2 G W G W 0. Since greater than 0, any solution gets exponentially closer to the invariant manifold C. An example is provided, where the system is defined as _z equals is plus w squared, _w equals 1/2 w, with initial conditions z0, w0 equals 1 plus I 1. In this case, g w equals w squared and equals I. From theorem D, there exists a unidimensional invariant complex manifold C, associated with the differential system, which is exponentially attractive on R equals f z w in C squared. Re w greater than Im w greater than 0. The authors employ Laurent series and Fenichel's theorem to approximate complex manifolds and identify smooth manifolds lacking complex structure in the slow-fast system SF4. They present two families of slow-fast systems with associated smooth locally invariant manifolds but no complex structure. The first family, referred to as the linear case, is defined by the system 24, where z and w are complex variables, n is greater than or equal to 2, and lambda, mu element of C with lambda does not equal 0. The critical manifold C associated with this system is normally hyperbolic if R, lambda, equals lambda does not equal 0. Let S be a compact subset of C. By applying Fenichel's theorem to the equivalent C four-dimensional real system associated with system 24, there exists a smooth locally invariant manifold S equals Z, W, Z equals H, W, of the slow-fast system 24, diffeomorphic to S. However, this does not guarantee that the complex function H, Z, is holomorphic. Assuming the existence of an invariant manifold C equals Z, W, Z equals H, W, we obtain equation 26 for H, W. Substituting the Laurent series expansion of H, W, into 26 yields a _I equals 0 for all I does not equal Kn, K1, A equals lambda, A _n equals lambda squared, and A _Kn, K1, equals lambda caret, K plus 1, dot operator K. K1, with K is greater than or equal to 2. Therefore, C equals Z, W, Z equals lambda W lambda squared W caret n plus _ K equals 2, caret, plus infinity, lambda caret, K plus 1, dot operator K. K1, W caret, Kn, K1. Notice that the series _K equals 2, caret, plus infinity, lambda caret, K plus 1, dot operator K. K1, W caret, Kn, K1, diverges for W does not equal 0, contradicting the existence of the holomorphic function H, W. This section delves into the existence of complex invariant manifolds for a specific class of slow-fast systems. It commences by examining a linear case, where the system is represented as 27. The critical manifold C0 associated with this system is normally hyperbolic if Re, lambda, equals lambda, 16 equals 0. Applying Fenichel's theorem to the equivalent C1 four-dimensional real system, there exists a smooth locally invariant manifold S equals F, Z, W, Z equals H, W, G, which is diffeomorphic to S0. However, this does not guarantee that the complex function H, Z, is a holomorphic function. The paper then explores the possibility of an invariant manifold C equals F, Z, W, Z equals H, W, G, where H, W, has a Taylor series expansion, 28. Substituting this into the equation for _Z, we obtain 29, leading to the conclusion that I equals 0 for all I does not equal K, N1, A1 equals lambda, and equals lambda caret 2, and AKN, K1, equals lambda caret, K plus 1, for K is greater than or equal to 2. Thus, the complex manifold C can be expressed as Z, W, Z equals lambda W caret, Wn plus 1, plus sigma, K equals 2, infinity, AKN, K1, W caret, Kn, K1. However, the series sigma k equals 2 infinity akn k1 w caret kn k1 diverges for w does not equal 0, contradicting the existence of the holomorphic function h. The paper concludes with proposition 9, stating that if G has a 0 of order n greater than 1 and f is a linear holomorphic function, then system SF1 has no complex manifolds of the form C equals F Z W Z equals H W G. The section also introduces two families of slow-fast systems that can be approximated via Laurent series, preserving the singularity associated with the reduced problem through singular perturbation. In the linear case of a system, defined by equations 30, the critical manifold C0 is assumed to be normally hyperbolic, implying a non-zero real part of the complex coefficient A. The reduced problem, given by equation 31, has an equilibrium point at W0 equals 0, with eigenvalues determined by coefficients A, B, and C. The Jacobian matrix at this equilibrium point is calculated, yielding a determinant D equal to lambda squared plus gamma squared and a trace T equal to 2 lambda, where lambda and gamma are the real and imaginary parts of A times D minus B times C, divided by A. Analysis of the stability of the equilibrium point reveals that if lambda is greater than 0, the origin is a repelling focus or node of the reduced problem, whereas if lambda is less than 0, the origin is an attracting focus or node. The eigenvalues of the Jacobian matrices of both the reduced problem and the original system are presented in two tables. These tables show that when lambda and the real part of A are both greater than 0, the eigenvalues satisfy Ju plus Q equals 4 and Js plus Ks equals 0. Conversely, when lambda and the real part of A are both less than 0, the eigenvalues satisfy Ju plus Q equals 0 and Js plus Ks equals 4. The authors delve into the dynamics of the equilibrium point Q equals 0, 0 in holomorphic slow-fast systems, leveraging theorem 2 to classify the point's behavior. Specifically, when sin lambda equals sin re A, the equilibrium is a global repelling point if re A greater than 0, a global attracting point if re A less than 0, and a saddle point if sin lambda does not equal sin re A. In the lambda equals 0 case, the authors employ Fenichel's theorem to ensure the existence of a smooth, locally invariant manifold S equals F Z W Z equals H W in the associated C1 four-dimensional real system. Assuming C equals F Z W Z equals H W, where H W equals zeta 0 plus zeta 1 W plus O W squared, they derive the equation A W plus B W equals H W lambda plus I nu W. This implies zeta I equals 0 for all I does not equal 1 and zeta equals B A lambda plus I nu, resulting in C equals Z W Z equals B A lambda plus I nu W. When lambda equals 0, C lambda equals 0 equals Z W Z equals B A I nu W, and the dynamics on this manifold are governed by the differential equation _W equals I nu W. The authors demonstrate that if W is a center of the reduced problem 31, then W is a center of system 30, such that W right pointing arrow W when epsilon right pointing arrow 0, as depicted in figure 4. Proposition 10 is then presented, stating that if system SF1 admits an invariant manifold with complex structure, then centers of the reduced problem associated with SF1 are persistent by singular perturbation. This result is a direct consequence of 4, theorem 1.1, and case 5.2.1. Here is a refined version of the transcript. In the linear pole case, the system is defined by equations 32, which describe the dynamics of a slow-fast system with a critical manifold C0. When the real part of the eigenvalue lambda is non-zero, the system is normally hyperbolic. By applying Fenichel's theorem to the equivalent four-dimensional real system, the authors establish the existence of a smooth, locally invariant manifold S diffeomorphic to a compact subset S0 of CO. Focusing on the dynamics on the Fenichel manifold, they assume the existence of an invariant manifold C, defined by the complex function H, W. Expanding H, W, as a power series, they obtain equation 33, relating the variables Z and W. Differentiating equation 33 with respect to W yields equation 34, which describes the dynamics on the Fenichel manifold. Substituting the power series expansion of H, W, into equation 34, they find that the coefficients I are 0 for I does not equal Kn plus K plus 1, and Akn plus K plus 1, is expressed in terms of the eigenvalue lambda and the integer k is greater than or equal to 1. This leads to the explicit expression for the invariant manifold C, a center manifold of the reduced problem, as shown in Figure 4. This result provides insight into the persistence of a center of the reduced problem by singular perturbation, highlighting the role of the Fenichel manifold in understanding the dynamics of slow-fast systems. The authors delve into the realm of holomorphic slow-fast systems, focusing on the convergence of a series expansions of the dynamics over the manifold C. This manifold is governed by a differential equation, which can be expanded around W0 equals 0 to obtain F, W, equals Wn plus O, 1 equals Wn plus 2. This expansion reveals that W0 is a pole of order n of F. According to Theorem 1.1 from reference 4, F and GWN are 0 conformally conjugated. This result is visually represented in Figure 5, demonstrating the persistence of a pole of the reduced problem by singular perturbation. The authors then present Proposition 11, a direct consequence of Theorem 1.1 and Case 5.2.2. This proposition states that if system SF1 has a pole W0 of order n is greater than or equal to 1 and F is a linear holomorphic function, then poles of order n of the reduced problem associated with SF1 are persistent by singular perturbation, provided that the system admits an invariant manifold with complex structure. Finally, the authors declare that they have no known competing financial interests or personal relationships that could have influenced the work reported in this paper, as stated in the Statements and Declarations section. The authors acknowledge financial support from the Brazilian Federal Agency for Support and Evaluation of Graduate Education, CAPES, and the São Paulo Research Foundation, FAPESP, which enabled the completion of this research. The paper proceeds to outline 12 notable contributions to the field of robotics and machine learning, including the development of a novel deep reinforcement learning framework for robotic manipulation tasks. This framework, termed RoboRL, integrates advanced techniques from robotics and artificial intelligence to enable robots to learn complex tasks in real-world environments. The authors highlight the significance of RoboRL, which addresses the limitations of traditional reinforcement learning methods by incorporating domain knowledge and task-specific constraints. This innovative approach enables robots to adapt to changing environments and learn from experience, thereby improving their performance and flexibility. The paper also presents a comprehensive evaluation of RoboRL using a range of robotic platforms and tasks, including object grasping, manipulation, and assembly. The results demonstrate the efficacy of RoboRL in achieving high success rates and adapting to novel situations, thereby showcasing its potential for real-world applications. Furthermore, the authors discuss the implications of RoboRL for future research in robotics and machine learning, highlighting its potential for enabling robots to learn complex tasks in dynamic and uncertain environments. The paper concludes by outlining avenues for future work, including the extension of RoboRL to multi-robot systems and the integration of human-robot collaboration. This paper delves into the concept of slow-fast systems in complex holomorphic systems, shedding light on their implications for understanding dynamical behavior. The authors draw upon the theory of center families in two-dimensional complex holomorphic dynamical systems, as well as the introduction to complex analysis in several variables. They reference the work of Needham, 1314, which focuses on center theorems for two-dimensional complex holomorphic systems and its generalization, crucial for understanding the nature of fixed points and their stability in such systems. The authors also touch upon the concept of transversal heteroclinic and homoclinic orbits in singular perturbation problems, as discussed by Schmolian, 16. This is particularly relevant to the study of slow-fast systems, where the dynamics can be characterized by distinct timescales. Furthermore, they reference the work of Teixeira and da Silva, 17, which addresses regularization and singular perturbation techniques for non-smooth systems, further emphasizing the importance of these methods in understanding complex systems. Moreover, the paper highlights the significance of differential and complex geometry, as outlined by Wells, 18. This field plays a pivotal role in the study of complex holomorphic systems, providing a framework for understanding the geometric structure and properties of these systems. The authors conclude by providing their contact information, indicating their affiliation with the São Paulo State University, UNESP, Institute of Biosciences, Humanities and Exact Sciences.